All right, moving on to example number 3. Before we go into example number 3, there is that section in your note package called reaction quotient. I would just skip over this for now. We'll come back to this maybe in the next lesson or tomorrow. So we're going to skip right into example number 3. And if you want, because we've done so many examples before, I think you might be able to try this one and maybe check your answer to make sure that you've got the right one. But essentially, what we're doing here is we are trying to figure out the equilibrium concentrations for each of the entities, including our gases. So our reaction here is the decomposition of carbon dioxide, so CO2 gas, double arrow. It decomposes to form carbon monoxide gas and O2 gas. The first thing I'm going to do is make sure that this is balanced. If I put a 2 here and a 2 here, that is sufficient to balance this out. And then when I read the question, I know that I'm given the initial concentration of CO2 gas. Because we're told that we have 0.250 moles in 1 liter, if I divide those two to get the concentration, my initial concentration is 0.250 moles per liter, right? If this liter value was anything other than 1, right, this would be a different concentration, because in this case, the moles divided by the liter gives you your concentration. Initially, we know that our carbon monoxide gas and our oxygen gas are going to be 0. In terms of our change, it is going to be corresponding to our coefficients, right? So because the coefficient here is 2, I know that the change is going to be minus 2x. And because I know that the coefficients here for carbon monoxide is 2, and it initially starts off with no concentration of it, it's going to gain, it's going to be plus 2x. And this has a coefficient of 1, so the change is going to be plus x. So at equilibrium, our carbon dioxide concentration, our expression is going to be 0.250 minus 2x. Our carbon monoxide concentration is going to be 2x, and our oxygen gas concentration is going to be x. Again, in this question, we are given our K value in the question, so we can use that to find our values of x by writing our equilibrium constant equation, right? So our K is equal to equation. Our K is equal to CO to the power of 2 times O2 to the power of 1 divided by CO2 to the power of 2. What I'm going to do is sub in whatever I can. So I know that my K value is in the question, so I'm going to plug that in. 6.40 times 10 to the power of negative 7 is equal to carbon monoxide gas at a concentration of 2x, all of that squared. So technically that will end up being 4x squared. O2 to the power of 1, which is just x, divided by 0.250 minus 2x, all to the power of 2. So if we take a look here, this is our equation. Remember what we did in our previous example? We had to do a check, right? And our check, or our test, is to compare the concentration to our K value. Let me choose a color here. So I'm going to do my test here. And we know that our concentration initially for carbon dioxide is 0.250 moles per liter, divided by our K value, 6.40 times 10 to the power of negative 7. So when I divide these two, 0.250 divided by 6.4 times 10 to the power of negative 7, I will end up with a number that is way larger than 500. I get a number that is 390,625, right? So this is greater than 500. So what can we do when we know that those two numbers, when you divide them, it's greater than 500? I can get rid of whatever the change is there. So remember, just as a recap from the previous example, what we're doing when we're comparing these two is seeing if the change is going to be of a significant value. What we know here is because these two numbers, when we're divided, it's greater than 500, I know that whatever this x value is, that is going to be a negligible value. So what I'm going to do is get rid of that and then do my calculations otherwise. So let's get to the rest of our calculations so we can solve for x. So here, 2x squared gives me 4x squared times x would give me 4x cubed. So I'm going to write 4x cubed divided by 0.250 squared. And I'm not including that minus 2x because when I divided the initial concentration by K, it was greater than 500. So I can make the assumption that whatever the change is going to be, it is going to be negligible. So with that, 6.40 times 10 to the power of negative 7 is my K value. Now notice how much of a difference this would have been. If I could not get rid of the minus 2x, so if this was not greater than 500, that my steps become so much longer. I have to do way more calculations. So when I keep going with my calculations, I might need a little bit more room here. So when I keep going with my calculations, I know that I end up with 6.40 times 10 to the power of negative 7 is equal to 4x cubed divided by 0.0625. And then when I take this over to the other side and multiply, I'm going to get 4 times 10 to the power of negative 8 is equal to 4x cubed. Dividing both sides by 4, I get 1 times 10 to the power of negative 8 is equal to x cubed. The cube root of this number is equal to 2.15 times 10 to the power of negative 3. Now that I know my x value, I can easily use that to find my concentrations at equilibrium. So let me just change the color here. Let's use purple. So to find the concentration of the CO2, I know that I have to take 0.250 minus 2 times 2.15 times 10 to the power of negative 3. And this change still gives me 0.250, right? That makes sense because remember the assumption that we made. We made the assumption that whatever change was taking place was going to be a negligible amount. Because that was the case, when I rounded, I would get 0.245, which I can round to 0.250. My concentration of carbon monoxide is going to be 2x, which is 2 times 2.15 times 10 to the power of negative 3, which will give me a number that is 4.3 times 10 to the power of negative 3 moles per liter. And lastly, my concentration of oxygen gas is just the value of x, which is 2.15 times 10 to the power of negative 3 moles per liter. So that was example number 3.